Welcome to the AP Physics 1 video lecture. This is covering the unit on momentum. The section is momentum and impulse. Let's take a look at what momentum is first of all. We can see that momentum is defined as the product of an object's mass and velocity. It describes the mass and velocity together linearly. What that means is this. P, which is momentum, is equal to mass times velocity. The unit for that is just kilograms times meter over seconds. From before, we had force, which is mass times acceleration. This is something like that, which is mass and velocity. Remember your kinematics equation where we talked about how an object moves in terms of its velocity and mass didn't really matter that much? Or when we talk about energy, when mass didn't really matter because things canceled out? Because mass matters when you want to talk about its momentum. The unique part about momentum is that momentum is a vector because it has velocity here. Velocity is also a vector. So sometimes you might see it with the arrow here that indicates that momentum is a vector. So here's the question. Which vehicle here has the larger momentum, the car or the truck? The answer would be the car or the truck. So the car here has a momentum of 4.32 times 10 to the fourth kilograms per meter second. And the truck has a momentum of 5.67 times 10 to the fourth kilograms per meter second. Here you are just plugging into the mass and the velocity, getting a value here. So we see here that the truck has a greater momentum. The reason why it has a greater momentum is because its mass is larger than the car. And also they are traveling the same speed. So this leads to the question, what can you do to the car so that it has the same momentum as the truck? There's multiple answers here. One, you can actually increase the mass of the car by 500 kilograms. Then it will bring the car's mass to 2,100 kilograms. Or you can increase its velocity to 35.44 meters over seconds to get its same momentum. Now we can take a look at this. You're going to rank from the largest to the smallest based on their momentum before the brakes are applied. To rank if it's equivalent, just stack them on top of each other. Okay, so let's take a look. So the two large ones are these, and if you multiply them, it should get you roughly 20,000 kilogram per meter second. Then the next is the yellow, the red, and the blue, which is 10,000. Then the last one, which is just 5,000. Okay. So here you're just multiplying it and it gets you their momentum. So two cars have the same momentum. Look at their mass and their velocity. So notice that although that blue car has a smaller mass, it went at a faster speed. So it has the same momentum. Let's look at momentum graphically here. Kevin can travel to work different ways. The distance versus time graph where the different ways are displayed. Which one does Kevin has the most momentum? Here, it's a distance versus time graph. So we know that momentum is P equals to mv. So you need velocity here. So biking will give Kevin the largest momentum because the slope of the distance versus time graph is larger for biking. So here you would say that the slope here is the largest one. So here it has the greatest velocity. That's the slope. The slope of the distance versus time graph is velocity. Therefore, Kevin will have the greatest velocity biking and in turn will have the largest momentum. So greater the slope of the distance versus time graph, that means a greater velocity. Greater velocity means greater momentum. In this case, because Kevin's mass is the same in all three scenarios. So, next, Kevin tracks and graphs his speed to work. Which graph did Kevin have the greatest momentum at t0? So at t0, we can look at here, we can look here, here, or here. Okay, there are two spots. It would be A and C. A and C, because the value of the speed is non-zero. So here we can say it can be 5 meters per second. Here, this can also be 5 meters per second. All right? Therefore, their momentum will also be non-zero at t naught as well. So at these two locations, Kevin's momentums are actually the same. This is the speed time. That's why you can look at a singular point. Now we want to look at momentum as it relates to force. These two are connected. The rate of change of momentum over time is equal to the net force applied to it. So delta P over delta T, that's the change of momentum over the change of time, is actually the force net on an object. So it's the same question now, but now we're going to see which graph does the most force from t naught equals to t0. So we can go from here to here, or from here to here. Okay, so if you want to look at its change, right? Graph A has the largest increase in the slope of velocity over time. Therefore, it will have the greatest acceleration. So this one, the acceleration would be greater. Acceleration of A is greater than the acceleration of C here. All right? Because the slope here, it curves like this. Right? So this behaves like an X, it just increases really fast. This one goes linearly. But now we want to look at the same graph, and now we want to ask, where is the momentum increasing the most from t naught to t0? So it's the same thing. We would have to look at its initial. This is going to be the initial momentum, and this is going to be the final momentum. Same thing here. Initial momentum and final momentum. And you can see here that delta P over delta T is equal to just, this is the initial, this is just the final P. So this can be final momentum minus the initial momentum. And if you divide that by delta T, you get this. You can factor the M out. You can see that V1 minus V0 is just delta V. Delta V over delta T is the same thing for A. So this is the formula for acceleration, right? So that's how you get the force involved. So in short, you can see this as the change in velocity, change in momentum can be defined by the force F equals to ma times delta T. So the amount of force multiplied by time can also give you the change in momentum. That's how these two are related. Here's the scenario. A ball mass 1 kilogram is initially moving to the right at 30 meters per second. After hitting the wall, the ball bounces and moves to the left at 20 meters per second. What is the change in the ball's momentum? Here's the formula. You plug it in. So you have a 30, which is the initial momentum, minus the final momentum, and this is going to be negative. So here, this is going to be 30, and the momentum afterwards, so this is here, this is not, negative 20. The reason why it's negative is because, remember, velocity is a vector. Velocity is a vector. So this is going positive, and then anything to the left is negative. That's why it's minus 20. So the change in momentum is 50 kilograms times meter second. So the change in momentum is actually large here. So the momentum afterwards is actually greater than the initial momentum going in. So the question, Sarah, after reading this last question, wants to know how much force did the ball did on the wall. What information does she need to answer her question? Well, we know from the last one that F net is equal to delta P over delta T. She wants to know force. So she wants to know. So this is her question mark. She has this. Okay. So F net is her unknown. She has delta P. So she needs the total time. So she needs the time factor. All right, and here you go. Delta T can just be seen as T if T not equals to 0. Let's look in change in momentum. We've seen this equation from our last problem, but we have a way to describe that delta P. That delta P, it can also be seen as the word impulse. Impulse, by definition, is the total change in the object's momentum. So you can see the formula as F net times delta T is equal to the impulse. Impulse is defined as the total change in the object's momentum. Note that the amount of force multiplied by time can also give you your impulse. So you can see this in two ways. The amount of force multiplied by time gives you the change in momentum, or you can say the amount of force multiplied by time can give you the impulse. Graphically, conceptually and graphically, what does impulse mean? So the tennis racket here strikes the ball. Both the ball and the racket strings are exerting forces on each other. So you have ball on racket and racket on ball due to Newton's third law. They are action-reaction pairs. If you graph this, you will see that the force as a function of time during a collision. F can be very large and typically in milliseconds. And it curves like this. It's never linear. So the force is generally never constant and often is variable in time. It's going to curve up, then curve back down. You can actually approximate that as an average force by multiplying by time is equal to the area under the curve. So here you could actually see that the impulse by multiplying, because what you can do here, just think about it here. So this can be length times width is equal to the area of a rectangle. All right. So assume this is a rectangle. You have the length, which is going to be time, and the width, which is going to be force. So the area under the curve of the force times time will give you impulse or change in momentum. Now you want to rank the change in momentum for these needed to stop. I'm going to give you the answer. This is 200 kilograms times meter second. There are 3, which is at 10,000 kilograms times meter second. And the last one, which is 5,000 kilograms per meter second. This is the same as before because to stop, P equals to 0. Momentum equals to 0 because velocity final was equal to 0. So the change in momentum was just its initial momentum. So let's graph this, right? So I'm going to graph this one. Okay? So its total momentum initially is at 10,000. So I'm going to make this 10,000. All right? Let's see, what's its mass? 5. So 1, 2, 3, 4, 5. Okay? And it's 20. So 2, 6, 8, 10. All right, so I'm going to make it like this. So this would be right here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this, I'm going to make this area here. This is going to represent my 10,000 kilograms per meter second. And in the end, its ending momentum would be its mass is the same. 1, 3, 4, 5. And it's completely flat. Okay, because it's zero momentum. So what was the impulse? Well, the impulse would be its change. And the change here would be what? Let's take a look. It has to be the same here. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. 3, 4, 5. Yep, perfect. So it would look like something like this. Because this is going to be your 10,000 kilograms per meter second. Right? If you add these two together, okay, you would get a final momentum of 0. All right? Let's even take a look at the calculation. Okay? So impulse. So that's delta P, which is impulse, is going to be equal to P final minus P initial. If you don't like that, I can change it for you. This can just be not P naught and P1. Better? Okay. So here you can add this. So so add P initial to both sides. So you get P initial plus change in momentum is equal to the final momentum. That's what we have here. Since the final momentum is 0, okay, we can say that the initial momentum is going to be equal to the negative delta P. Okay? So, because this is going to go to 0. Right? Then you're going to subtract delta P to both sides. Right? That's why the impulse here has to be negative. All right? Change in momentum. Rank from the largest to the smallest based on the magnitude of the force needed to stop them. This is actually a trick question. There's not enough information because here it was F net is going to be equal to delta P over delta T. You're going to need time for this. Last question. This is the momentum and energy question from a scenario from the FRQ of the AP Physics 1 exam. All right? Here you could read the scenario to yourself. A 4.0 kilogram block is initially at position x equals to 0 and in contact with an uncompressed spring k equals to 2 of a negligible mass. The block is pushed back along a frictionless surface from position x equals to 0 to x equals to negative 5 meters. The block is then released. Right at x equals to 0, the block has its maximum velocity, then enters a rough part of the track and eventually comes to rest at a position x equals to 15 meter. The coefficient of friction of the rough track is mu equals to 0.25. What is the potential energy of the block spring system? So UG is equal to 1/2 k delta x squared. That is the potential energy of a spring. Plug in the values, you get 25. The units here would be joules. What is the maximum velocity? So right here, this is when all the gravitational potential is going to be equal to the kinetic at this point. So the 25 joules is going to be equal to 1/2 mv squared. Solving for v, you get v equals to 5 meters per second. Why does the block stop at v naught? V naught equals to 0. So why does it stop here? Why does it stop here when v1 equals to 0? Okay. It stops because all the kinetic energy is transferred out of the system in forms of thermal. So how much work? So we can say that this stops, okay? So there has to be a net force here, okay? A net force has to be done here. Or you can say that work is done here to stop the block because energy is coming out of the system. So to do this, work is equal to force times distance. The force here is the force of friction that is doing work. Okay, you have the distance, which is 15 meters. It comes from the start of the rough track to the end of the rough track, which is 15 meters. You need to know the force of friction. Well, what's the issue here? Well, we can get force from our change in momentum equation that we just learned. Friction force times delta T is equal to the change in momentum. So here's my equation. Here are my parts for it. Okay, the issue is I need delta T. We can see from the car example, you need delta T to do the force, to get the force. So you have to actually use your kinematics equation. This is the classic kinematics equation. Delta x is your position equals v naught t plus 1/2 at squared. A equals to 0 because there's no acceleration in the horizontal. So the position is equal to velocity times time. Plug it in, you get t equals to 3 seconds. Now you have 3 seconds. You can plug it back in here, getting you 6.67 newtons. After that, you can plug it back into the work equation, getting you work equals to 100 joules. This is a good problem to see how kinetic energy, force, and momentum all connect. Here you go. This is your lecture on momentum and impulse.